A river delta is still visible inside Jezero crater, on a planet where rain no longer falls. Did ancient Mars keep its life-making ingredients together long enough for biology to begin? But water is not the same as time. A river channel proves water moved. A clay mineral proves water changed rock. But no clue alone proves Mars stayed habitable long enough for life to begin. Life may not need a perfect planet, but it needs a working sequence that lasts after the first promising moment passes. We are not asking whether ancient Mars had ingredients. It did. We are asking whether the ingredients overlapped, cycled, and endured. This question needs a careful path, so we are going to work through it properly. By the end of this video, you will understand why ancient Mars may have had real habitable windows, and why the unresolved question is whether any one window stayed open long enough to become biology. If you enjoy exploring questions like this with us, subscribing helps others find them too. Sharing the video helps even more. Let's begin. Start with the picture Mars gives us, because it is hard to resist. A planet that now sits cold and red once carried water through valleys. Rivers cut across ancient highlands. Deltas built outward into crater basins. Minerals formed in contact with liquid water. From a distance, the evidence seems to pull in one direction. Ancient Mars was not always the world we see now, and that is true, but the public image of blue Mars can move faster than the science. One moment we are looking at valleys, the next moment we are imagining shorelines and clouds, rain and maybe even life waiting just beyond the frame. The mind fills in what the rocks themselves do not say. Mars invites that mistake because it is close enough to feel comparable. It has a day almost the length of ours. It has polar caps. It has volcanoes and canyons. It has dust storms and dried river systems. Compared with Venus or the outer moons, Mars feels almost readable, almost familiar, and almost familiar is exactly where the confusion starts. Jezero crater is a perfect example of this tension. Perseverance is exploring a place chosen because it once held a lake and a delta. Water entered the crater. Sediment settled. Layers formed. Fine-grained material may have preserved chemical clues. If you wanted a place on Mars where old habitability might have left a record, Jezero belongs near the top of the list, but Jezero is not a photograph of a living shoreline. What remains is a preserved end state. The water is gone, the lake is gone, the delta is rock. The clue survived, while the environment itself vanished billions of years ago. We are reading the closing page of an environment whose middle chapters we can only reconstruct. Gale Crater pulls the story in a different direction. Curiosity has climbed through sedimentary layers that record ancient lake environments, changing minerals, and chemistry that once could have supported microbial life. That matters because Gale is not just one splash mark. Gale gives us sequence. Layer after layer tells us Mars could preserve environmental change across geological time, and yet sequence is still not the same as continuity. Think of a stack of pages torn from a book. You can read scenes from the story without knowing how much is missing between them. Ancient Mars is like that. We have preserved episodes. We have mineral clues. We have landforms shaped by flowing water. But the life question asks for something more demanding than proof that water appeared. It asks whether water stayed useful. A river can run after a thaw, after an impact, or after a volcanic pulse. It can also run after a climate swing, or under a sky that allowed seasonal melting. Each path leaves a different kind of biological opportunity. A short flood can carve. A longer lake can sort sediment. A stable groundwater system can protect chemistry from the surface. A shoreline that wets and dries can concentrate molecules. The same word, water, covers all of that. Here's why blue Mars is so seductive and so dangerous. It turns many different processes into one emotional picture. We see the color blue and we borrow Earth's meaning for it. On Earth, water is wrapped into almost every living system. Our planet trained us to treat water as an invitation, but that training does not transfer cleanly to another world with a different size, atmosphere, and history. Mars asks for more discipline. Picture what the real ancient Mars may have looked like spread across its full history. Wet in places, dry in others. Frozen for long stretches, briefly thawed, chemically active underground. Quiet at the surface, uneven through time. A map of all its watery evidence might look rich when compressed into a single image. Spread those clues back across millions or billions of years, and the picture becomes less like an ocean world and more like a planet with openings. Some openings may have mattered. Some may have been too brief. Some may have been well protected but isolated. Some may have been chemically promising but hostile in another way. The question is not whether the doors opened. The question is what happened while they were open. Think of a dark house in winter. A door opens and warm air moves through one room. For a moment, the room changes. If the door closes immediately, that warmth is only an event. If heat keeps returning and the room holds it, the event becomes a condition. Mars shows us many signs of events. We are trying to find conditions, and that difference sharpens the whole picture. Ancient Mars was not boring. It was not obviously hopeless. The frustrating thing is that it may have been close enough to build deltas, close enough to alter minerals, close enough to store organics in ancient rocks, close enough to make serious scientists send rovers to read its sediments across decades of missions. But close is not the same as enough. A planet can carry the marks of habitability without ever crossing into biology. It can have the pieces in the wrong order. It can open promising environments too far apart. It can reset chemistry before fragile systems gain memory. It can preserve water-shaped geology while losing the duration that made the water biologically useful. So the first lesson is plain. Ancient wet Mars is not the answer. The evidence lets us ask the better question. Did Mars have moments, or did it have continuity? Everything else follows from that. Look at the picture from another angle. Mars is the only nearby world where a lost watery past still feels close enough to touch. Venus hides behind clouds and overwhelming heat. Europa and Enceladus hide their oceans under thick ice. Titan is chemically strange in ways that feel almost alien before the life question even starts. Mars gives us dry riverbeds in sunlight. It gives us rover tracks beside layered stone. It gives us a dead surface that still looks geologically literate. But that closeness can make us impatient. We want the planet to translate itself into familiar language. River, lake, shoreline, life. The translation is imperfect. A Martian river did not necessarily sit under an Earth-like sky. A Martian lake did not necessarily have a stable climate around it. A Martian delta did not necessarily belong to a long-lived water cycle. Each familiar shape may have formed under conditions that would feel strange, brief or cold, perhaps salty or acidic, perhaps buried or intermittent. So the first act of discipline is emotional. We can admire the evidence without letting it make promises on behalf of the planet. A valley network is not a living stream. A clay deposit is not a microbial mat. A crater lake is not an ecosystem. They are clues, serious clues, the kind of clues worth building missions around. But they point to environments, not conclusions. Here's why the old phrase, "follow the water," was both powerful and incomplete. It gave Mars exploration a direction. It found the right kinds of rocks. It moved science away from random searching and toward places where past environments could be tested. But once the water is found, the next question begins. Follow it where? For how long? Through what chemistry? Into what shelter? Back again, or only once? The sharper Mars story begins after the slogan has done its job, and one more caution belongs here before we go deeper. The most famous images of ancient Mars are reconstructions. They are useful because they make invisible history visible. But a reconstruction is an argument in visual form. It chooses assumptions about climate, atmosphere, and ice. It chooses a water level and a sky. Change the assumptions and the same terrain can become a colder world with lakes under ice. It can become a drier world with short-lived floods. Or it can become a mixed planet where some basins hold water while others remain frozen. So we should treat every blue Mars image as a doorway, not a destination. It brings us into the evidence. It does not settle the evidence. The real planet sits behind the picture, harder and more interesting. Its color is not the key, its timing is. But there is one more calibration we owe the evidence before moving on. The valley networks are not evenly distributed across Mars. They cluster in ancient southern highlands, terrain that dates from billions of years ago. They are rarer on younger surfaces. That pattern matters because it suggests the conditions that produced running water were strongest in an earlier era and then changed. Geologically, we can say something declined. What declined is still part of the debate. It may have been a thick early atmosphere, a warmer climate, or changing volcanism and impacts. But the timing itself is a constraint on the life question. If Mars had its best surface water early, and the chemistry of early life also needs meaningful time, then the two clocks have to run together. Were the best hydrated environments also old enough and stable enough for chemistry to progress? An ancient lakebed is not automatically useful for life just because it is ancient. It has to be ancient in the right way, preserved, not just dated. So consider what a geologic map of ancient Mars shows. It shows regions where water once acted on rock. It shows minerals formed in wet conditions. It shows landforms carved, filled, and altered by flowing and standing water. What it does not show is the duration of each event. A valley that took 1,000 years to carve looks the same in rock as a valley that took 10 million years. Chemistry is not written on the surface of the sediment the way age is. For that reason, the most important rovers do more than photograph landscapes. They examine chemistry, texture, and mineralogy. They also examine layer relationships. They try to read the clock that erosion and deposition cannot show directly, and there is a scale shift that helps here. We tend to think of ancient Mars at orbital distance, a surface mapped from above. But the life question happens at a different scale entirely. It happens at the scale of a rock face, a mineral grain, or a chemical video. It may happen in a shoreline pool or a fracture where fluid moved through rock. Chemistry operates there. Duration becomes relevant there, not only in millions of years, but in reaction cycles and returning seasons. The challenge of Mars science is translating between those scales. An orbital map can show a lakebed. A rover can examine its chemistry. Neither alone can tell us whether the right conditions persisted for the right length of time at the right scale for life-relevant chemistry to progress. Think of trying to answer whether a house was ever comfortable to live in by looking only at its exterior walls. Some clues survive: the shape of a door, the evidence of a fireplace, and the placement of windows. But comfort is interior: heat in winter, dryness in summer, and food on a table. A rover inside the house can tell us more. Were the floors level? Could the hearth hold fire? Was the roof tight? But even the rover cannot tell us whether anyone was ever home. We are building an understanding of Mars that is honest about what the landforms show, and honest about what they cannot confirm. The valley networks and deltas tell us water was there. The mineral record tells us conditions once existed that we associate with habitability. But habitability is only a word for the possibility space. Inhabitation is a different event, and to evaluate whether inhabitation was possible, we need to go beyond what water proves, which is the next step. A delta is one of the clearest signatures a planet can leave. Water enters a basin. The current slows. Sand, silt, and clay settle out. Layer by layer, a fan grows into the standing water. Seen from above, the shape is almost a confession. Something flowed here, and it carried the ground with it. On Mars, that matters enormously. Valley networks tell us liquid water moved across or near the surface. Deltas tell us water transported sediment into lakes or basins. Lakebeds tell us standing water existed long enough for layers to accumulate. Clays tell us rock and water interacted under conditions that changed minerals. Sulfates tell us other kinds of watery chemistry happened too, sometimes under evaporation, acidity, or later alteration. And none of that is weak evidence, but the mistake is treating strong evidence for water as strong evidence for life. Water proves that Mars crossed one threshold. It does not prove that Mars crossed all the thresholds stacked behind it. A habitable environment is not just a wet environment. In the strict sense, liquid water, useful chemistry, and energy must come together under protection long enough to support life as we understand it. Even the word habitable has to be handled carefully. When scientists say an ancient Martian lake was habitable, they usually mean it had conditions that could have supported certain kinds of microbial life if life had been there. They are not saying life began there, they are describing possibility within evidence. The word is a description of a setting, not a verdict about its history. Gale Crater shows why the distinction matters. Curiosity found sedimentary rocks laid down in ancient water-rich environments. The chemistry included ingredients and energy conditions that on Earth can be associated with microbial habitability. Organic molecules were detected in ancient rocks. That finding is extraordinary, but organic molecules are not organisms. Organic chemistry means carbon-bearing chemistry. Living things can make it, so can non-living processes, meteorites or geologic chemistry. In Gale, organics matter because they show carbon chemistry could survive on Mars over billions of years. They widen the possibility space. They do not close the case. The same discipline applies to clays. Clay minerals can be friendly to preservation. They can trap and protect chemical information. They also form through water-rock interaction, which tells us something real about past conditions. But a clay-bearing rock is not a biosignature just because clays on Earth can sometimes preserve biology. The mineral is a witness. The mineral is a witness, not a narrator. Evidence has lanes. A valley tells us about flow. A delta tells us about sediment and standing water. A mineral tells us about chemistry. An organic molecule tells us about carbon preservation. A layered rock tells us about sequence. Each clue is powerful. Each clue is partial, and the life question lives in the space between them. So the duration question begins when we ask what sits between the clues. How long did a lake persist before drying or freezing? We have estimates for specific sites, but the uncertainty is wide. Did water return often enough to matter? That depends on the climate model, and the models disagree. Did the chemistry remain mild, or did it swing through destructive states? The mineral sequences suggest both happened. Were organics buried and protected quickly, or exposed to radiation and oxidation? The answer differs by location, depth, and era. Look at the phrase "Mars had water" from this angle. It sounds like a condition. Often the evidence may be recording episodes. Water appeared, worked briefly on the rock, and then left the landscape to dry or freeze. Episodes can still matter. A brief wet period is not automatically irrelevant. Some prebiotic chemistry may benefit from cycles, wet phases that move ingredients and dry phases that concentrate them, mineral surfaces that organize them, and renewed water that carries products forward. A perfectly static pond is not the only possible path, but useful cycling is different from random interruption. If each wet phase is followed by freezing, oxidation, or burial, then the system keeps starting over. If the ingredients never meet in the same place at the same time, then the planet can look rich from orbit and still fail to produce a working chemical sequence. Here's where Mars becomes more subtle than a simple checklist. Water is necessary for life as we know it. Carbon chemistry matters too. So do energy flow, and protection from destructive conditions. Above all, time has to be arranged in the right way, not just as a long number on a timeline, but as a useful order. Imagine trying to build something fragile on a beach where the tide comes in once, drops a pile of parts, and then never returns. One version gives Mars an opportunity. Picture the tide coming back every day instead. It moves some parts and concentrates others. It leaves films on rock, dries shallow pools, and wets them again. The second version gives Mars a different kind entirely, and then picture storms repeatedly smashing the whole structure before it can become anything. All three leave evidence of water. Only some might support progress towards something more organized. So when we look at Mars, the honest question is not whether there was water. The answer is yes, in many places and forms. The honest question is what the water was doing through time. Was it building environments or only leaving marks? Was it connecting chemistry or scattering it? Was it protecting fragile compounds or exposing them? And this is exactly why Jezero and Gale matter so much. They are not magic places because they guarantee life. They are valuable because they preserve context. A delta records transport into a basin. A sedimentary mound records layers. A rover can examine minerals, textures, and organics in relation to each other. It can also place chemical alteration in context. Context is what turns a clue into a story. But even context has limits. A rover reads a tiny part of a crater on a planet-wide surface. Orbital maps show patterns, not every missing interval. Billions of years of impact and erosion, radiation and burial, chemical alteration and atmospheric loss stand between the ancient environment and the present sample. So water proves the beginning of the case. It proves that Mars was not always the dry planet we see now. It proves that some environments crossed into the realm of serious habitability. It gives the search for life its scientific foundation, but it does not tell us whether the foundation ever supported a house. Think of the evidence as a ladder. The first rung is geomorphology, the shape of the land. Channels and valleys tell us water-shaped terrain. Fans and basins add the shape of standing or slowing water. The second rung is mineralogy, the chemistry locked in rock, telling us what conditions altered the crust. The third rung is environmental reconstruction, lakes and streams, groundwater and evaporation, then their timescales. The fourth rung is habitability. Only after climbing those rungs can we ask what life might have done there. The trouble starts when storytelling jumps from the first rung to the fourth. Here's the practical implication. Minerals are witnesses, not narrators. Clay formation tells us about water-rock interaction. Sulfates speak to changing chemistry and evaporation. Silica can preserve fine textures in some settings. Carbonates record exchanges between atmosphere, water, and rock. But minerals form in particular chemical windows and can be altered later. Reading them requires exactly the kind of patience that makes Mars science slow and strong. For the missing variable, we have to look not just at the water itself, but at what the water was allowed to do through time. And that question leads us somewhere that feels even harder. One specific example from Gale Crater helps put the mineral argument in focus. Curiosity's early investigation at Yellowknife Bay revealed a mudstone called the sheepbed member. The chemistry there included iron and sulfur minerals, clay minerals, and neutral pH water. Evidence of ancient groundwater added another layer. Scientists described it as a habitable environment, not as a place where life existed, as a place where microbial life, had it been present, could potentially have survived and drawn energy from its surroundings. The careful phrasing carries the whole lesson. Could have survived, had life been there. The statement describes environment, not occupancy. The rock does not say whether life arrived. It says the conditions passed a scientific threshold for habitability. What Yellowknife Bay also showed is that not all ancient Martian environments are equal. Some are more chemically promising than others. Some preserve better than others. Some have multiple lines of consistent evidence pointing toward habitability, while others have only one or two. Gale elevated the conversation by showing that Mars was not uniformly bland chemistry. It had specific, interesting places, but even within Gale, conditions changed. As Curiosity climbed Mount Sharp, layers shifted from clay-bearing environments to sulfate-bearing environments. That transition records a change in the ancient environment. Perhaps drying, perhaps acidification, perhaps a change in how water interacted with rock over time. A habitable condition in one era gave way to a different, possibly harsher condition in another. The same body of rock records more than one chapter. That layered history is part of what makes Gale scientifically important. Not just a snapshot, but a sequence. And a sequence helps constrain the life question in a way a single sample cannot. How long did the habitable conditions persist before the shift? What caused the shift? Were conditions after the shift still potentially habitable in some ways? Or did they close completely? Those questions have partial answers. Some intervals within Gale appear to have had more favorable chemistry for longer than a brief flood event would produce. Layered mudstones form through sustained deposition in quiet water. They are not the product of a single storm or a flash thaw. They represent time. Exactly how much time remains uncertain. Whether it was continuous or punctuated remains a subject of ongoing research. So water proves more than presence. In the right context, it can prove something about duration. A mudstone requires sustained settlement. A delta requires repeated transport. A graded sequence of minerals requires changing conditions over meaningful spans. Water as a medium for those processes carries duration embedded in its products. But still, duration within a lake or sequence of deposits is a local clock. It tells us about one environment. The bigger question asks whether the planet's history as a whole gave those local environments enough time to be relevant, and whether they were connected across enough space and time to matter biologically. Think of it this way. Yellowknife Bay shows us a habitable moment in Mars history. It says, "Here once there was chemistry that life could use." What it cannot say is whether that moment was a strand in a larger useful sequence, or an isolated room in a building that was otherwise empty and cold. Answering that question requires understanding what surrounded the local moment, the climate that allowed it, the processes that ended it, the paths that continued or closed afterward. Minerals are honest witnesses. The next task is to ask them about duration more precisely, and to do that, we have to reckon with the first hard constraint on ancient Mars. Not the chemistry, but the energy that would have powered and sustained any warm surface environment at all. The missing variable is time, but not time in the simple way. It would be convenient if science gave us a single number. 10,000 years of liquid water, 10 million years of groundwater, 100 million years of stable lake chemistry. Put the number beside Mars, compare it with the length of each wet period, and decide whether the planet had enough. We do not have that number. Earth tempts us to think we do. Life appears early in our planet's preserved record, at least on geological timescales. That can make biology seem almost inevitable once conditions become suitable. But Earth's earliest history is incomplete. The oldest rocks have been heated, buried, and deformed. They have been recycled and argued over for decades. Evidence from that era is precious and genuinely difficult to interpret. Earth tells us life can arise early on a habitable planet. It does not give Mars a stopwatch. Mars had a different size and gravity. Its interior heat, atmosphere, and magnetic history followed another path into cold dryness. Even if life began quickly on Earth, we cannot export that timing across space and call it a rule. The two planets ran different experiments under different constraints. So the phrase long enough has to mean something richer. It means repeated chances without total reset. Chemistry that can carry products from one step to the next. Water that appears in useful relation to minerals and energy. Concentration, not endless dilution. Protection from conditions that would break fragile molecules apart. Environments that do not disappear every time the next ingredient arrives. Now, in origin of life thinking, sequence matters enormously. Raw ingredients do not assemble themselves just because they occupy the same planet. Carbon, nitrogen, and phosphorus have to be arranged into pathways. Sulfur and minerals have to join the right chemistry too. Water and heat must connect them to useful gradients. Some molecules need to form. Some need to be selected or concentrated. Some need surfaces or compartments. Some need cycles. A shoreline might help because wet and dry phases do different work. Wet phases dissolve and transport. Dry phases can concentrate. Minerals can hold molecules in place. Re-wetting can move products onward. Other settings have their own advantages. Freezing can concentrate solutes into tiny pockets of brine. Hydrothermal systems can provide gradients and energy, but every helpful cycle has a destructive mirror. Drying can concentrate, or it can strand chemistry where nothing continues. Freezing can organize, or it can lock reactions away entirely. Oxidation can drive useful chemistry, or it can destroy organics before they accumulate. Impact heat can create a temporary lake, or it can sterilize and disrupt everything around it. Burial can protect a signal, or it can isolate a habitat from the energy it needs. And that is why time alone is not the whole answer. 1,000,000 years of the wrong conditions may do less than repeated shorter cycles in the right setting. A lake that lasts a long time but remains chemically poor might be less important than a smaller system where water and rock, energy and concentration meet regularly. A brief warm pulse may be geologically dramatic but biologically useless if nothing survives the return to cold. What we are asking is whether Mars had productive time. Productive time has memory. One step leaves something the next step can use. The environment changes without erasing everything. Molecules do not have to begin from scratch after every thaw or flood. Energy returns. Water returns. Minerals stay available. Protection persists long enough for fragile products to accumulate, and that is the deep difference between a planet with ingredients and a planet with a recipe. An ingredient can exist anywhere. A recipe needs order. Mars may have had many ingredients scattered through space and time. Water in one era, organics preserved in another deposit, redox chemistry in one crater, hydrothermal energy in a separate setting, protective clays in a basin that later dried, groundwater below a crust that surface missions can barely touch. Compressed into one description, that sounds like abundance. Spread back across Martian history, it may be fragmentation. The ingredients may have existed, but never in the same place at the same time for long enough. Here's why the title question carries real weight. Did Mars have everything needed for life except enough time? Sounds almost simple. The harder version asks whether the right conditions overlapped long enough in the same environments. Did constructive cycles continue without being repeatedly broken? And the answer to that question is genuinely open. The word early also holds a psychological trap. We say life appeared early on Earth, and the phrase compresses enormous uncertainty. Early compared with the age of the planet can still mean spans too large for human intuition. The young Earth was not a laboratory with a start button pressed at day one. It was bombarded and cooling, differentiating and forming oceans, recycling crust and changing atmosphere. The evidence that survives from those first chapters is fragmentary. So when Earth is used as a comparison, it should humble us. Earth proves that life can emerge on a rocky planet. It proves that once life is established, it can become astonishingly persistent, but it hides the exact pathway. We do not know how many failed chemical experiments came before success. We do not know which cycles were essential and which were incidental. Mars may have had less margin. Smaller planets cool faster. Mars lost much of its early atmosphere and surface water. Its magnetic protection faded. Its surface became colder, drier, and more exposed. If Earth had a broad, forgiving stage for prebiotic chemistry, Mars may have had narrower stages with harder closing times, but narrower does not mean impossible. A narrow window can still matter if it is the right window. A protected hydrothermal system might maintain chemistry while the surface freezes. A crater lake might preserve cycles long enough to generate real complexity. The question is not whether Mars copied Earth. It almost certainly did not. The question is whether Mars found its own way to keep a sequence alive. So enough time should never be heard as a single number. It becomes a structure. It asks whether the environment had recurrence, memory, and protection. Recurrence brings ingredients back together. Memory lets chemical products survive into the next phase. Protection keeps destructive forces from erasing everything before progress can accumulate. Look at what those three requirements mean for Mars. If any environment had recurrence, memory, and protection together, the life question remains open in a serious way. It only needed to happen somewhere, at some point in the planet's history. If no environment achieved all three, then even a wet Mars could have been a planet of interrupted beginnings, and that sets up the next constraint we need to face. Because the surface evidence points toward water, but the sky above ancient Mars gives us a hard physical problem. The Sun was weaker. Origin of life research is relevant here, not as a direct answer, but as a clarification of what questions to bring to Mars. One active area of investigation looks at wet-dry cycling on mineral surfaces. In certain experimental settings, when organic molecules are deposited on mineral surfaces and then cycled through wet and dry phases, interesting chemical steps can occur. Molecules can concentrate. Some can link into longer chains. Mineral surfaces can organize and protect compounds in ways that matter for later steps. This does not prove that life arose this way. And it does not mean Mars had the right conditions, but it illustrates that the conditions for productive chemistry are specific. A lake where chemistry is permanently diluted may do less than a shoreline where cycles concentrate, organize, and advance. A different research thread focuses on hydrothermal vents, where sustained chemical gradients and mineral surfaces provide a constant source of energy-releasing reactions. The appeal here is duration and protection. The gradient does not dry out. It does not depend on a sunny day. Rock chemistry powers it, and can continue as long as the heat source persists. On Earth, some researchers think early life found this kind of niche more useful than a surface shoreline. Neither model is ruled out on Mars, and neither model is confirmed. What they share is a set of requirements that go beyond ingredients. They both require sequence. They require an environment that does something useful after the initial state, rather than only remaining stable or cycling without direction. A hydrothermal vent that provides energy but lacks the right mineral surfaces may miss a step. A wet, dry shore that cycles but never concentrates the right molecules may complete no useful work. The chemical work we are asking about involves some of the hardest steps in all of chemistry. Forming RNA or its precursor, making membranes that can contain chemistry, generating the first self-reinforcing reaction cycles. We do not understand these steps well enough on Earth to specify their minimum requirements on Mars, but we understand enough to say that each step needs a specific environment, and environments that pass requirements for one step may fail requirements for another. Phosphorus deserves a sentence here, because it is one of the sharpest constraints. On Earth, phosphate is critical to DNA and RNA, to ATP and membrane chemistry. Its availability in early Earth chemistry is an active research problem. On early Mars, phosphate exists in rocks. Curiosity found evidence of it. But dissolved phosphate in ancient water bodies depends on specific conditions. pH matters, competing ions matter, local rock chemistry matters, in ways we have only begun to study for Martian settings. So the ingredients exist in principle. Whether they were accessible in the right form and concentration, at the right time and in the right settings, that is a different and harder question. When we say the missing variable is not duration alone, but productive time, that distinction matters. Productive time is not a number, not a count of years, but a structure of overlapping conditions. An environment has productive time when the chemistry from one phase carries over into the next, and cycles build rather than erase, when protection persists long enough for fragile products to stabilize, and when the energy supply continues without catastrophic interruption. A lake that exists for 1,000,000 years but cycles through chemistry without accumulating anything is not offering productive time. Only 1,000,000 years of activity that leaves no chemical memory. And that concept matters for how we read Mars. When we ask whether Mars had enough time, we are asking whether any Martian environment structured time productively. Not just whether time passed, but whether something useful accumulated inside it. So the real missing variable on Mars is not just years, it's whether time was used. And now the question becomes concrete. Did any Martian setting, a lake or hydrothermal vent, a groundwater system or mineral surface, have the right structure to use time? That depends on factors we are still working to understand. What the climate allowed, what the energy budget permitted, what the mineral chemistry provided, and the climate question begins in the sky, not the rocks. The river record has to face the sky. Early in solar system history, the sun was roughly 70 to 75% as bright as it is today. That problem matters for Earth, and it matters even more for Mars. Mars orbits farther out. Even now, it receives much less sunlight than Earth does. In the deep past, under a fainter young sun, keeping liquid water stable on the surface becomes physically difficult, so we call it the faint young sun problem. And it is not a detail hidden in climate models. It's one of the central contradictions of ancient Mars. The rocks say liquid water moved. The energy budget asks how. If Mars had rivers, lakes, and long-lived surface water, something had to compensate. A thicker atmosphere could trap heat. Carbon dioxide could provide greenhouse warming. Additional gases such as molecular hydrogen may have helped under certain atmospheric conditions. Clouds might warm or cool depending on their properties. Volcanism, large impacts or orbital changes could create temporary episodes of melting. Every solution has a cost. A globally warm, wet Mars is attractive because it makes the geology feel intuitive. Rain falls, runoff cuts valleys, lakes fill, groundwater circulates, sediments accumulate. The public picture almost writes itself, but a warm, wet Mars has to stay warm under a weak sun. It needs a greenhouse strong enough and durable enough to matter. It has to avoid freezing too often. It has to explain how atmosphere was maintained, how heat was trapped, and why the chemical traces of that ancient atmosphere look the way they do today. A cold, icy Mars has the opposite appeal. It fits the faint sun more comfortably. The planet can stay mostly frozen, with ice stored at the surface or near it. Then impacts or volcanic episodes, orbital changes or other warming events melt some of that ice and create runoff, so the physics becomes easier, but the biology becomes harder. A transient melt can move sediment, it can carve a channel, it can fill a crater lake for a time. But if the warm period is short, the habitable window may close before chemistry progresses. If wet episodes are separated by long frozen intervals, the planet may build a dramatic geologic record from events that were biologically disconnected, events that never had the chance to build on each other. Here's the deeper point. The climate debate is a time debate. We are not choosing between two paintings of Mars. We are choosing between different meanings for the same evidence. A valley formed under a long hydrological cycle implies one kind of planet. A valley formed by repeated short melt events implies another. Both can leave water-shaped terrain. They do not offer the same chance for life. Now imagine standing on early Mars under that dimmer sun. The difference is not just cold air, it is everything cold does to a habitable pathway. Water freezes or retreats. Chemical reactions slow. Surface environments become more exposed and intermittent. Lakes may be covered by ice. Groundwater may remain protected, but harder to connect to surface chemistry. Wet moments become precious because they are rare, and rarity can concentrate the question. If warm periods were brief, Mars needed them to do a lot of work. Water had to flow, dissolve, and transport. Then chemistry had to react, concentrate, and preserve something useful, perhaps more than once. A single flood could reshape landforms, but life's beginnings likely need more than one dramatic rearrangement. They need conditions that carry forward, building on each previous phase. Climate models try to test these possibilities. They ask what gases, pressures, and clouds could produce liquid water. Then they test what surface conditions and solar inputs were needed. They test whether a thick carbon dioxide atmosphere is enough on its own. They explore whether adding other gases changes the outcome. They ask whether mostly ice-covered worlds can still make rivers during episodes. But the models are not enemies of the rocks. They are the way the rocks are forced to obey physics, and the physics keeps pushing back against the simple story. A warm, wet Mars may explain some landforms cleanly, but sustaining that warmth is hard. A cold, icy Mars may satisfy the energy balance, but then the evidence for widespread fluvial activity becomes harder to produce and harder to translate into biology. Mars seems to ask for water with one hand and take warmth away with the other. The habitability question sits between those hands. If the planet solved the faint young sun problem for long intervals, then ancient Mars becomes a more serious candidate for sustained surface habitats. Lakes could last, groundwater could circulate, chemical weathering could continue. Environments might connect across basins and regions. If the planet solved the problem only in bursts, then the word habitable becomes narrower. It means temporary opportunities, not a stable planetary condition. It means local windows rather than a broad and forgiving stage. Both versions are scientifically interesting, but only one gives time easily. So look at what that means for the Martian rivers we started with. They are not just traces of a lost paradise. They are evidence at odds with a cold energy budget. Every channel becomes a question about heat. Every lakebed becomes a question about duration. Every delta becomes a question about whether the basin lived as an environment or flashed briefly into usefulness before freezing over again. And the obvious greenhouse answer brings us to the next problem. The faint sun also changes how we imagine ancient skies. A warmer Mars cannot be painted into existence by adding clouds and rain. The atmosphere must have had enough pressure and composition to hold heat, permit liquid water, and survive long enough to explain the geologic record. It must also fit what we know about atmospheric escape and volcanic outgassing, impact erosion and chemical deposits. Add more carbon dioxide, and greenhouse warming improves up to a point. But condensation and other effects can complicate the result at higher pressures. Add molecular hydrogen, and warming may become easier under some models, but then you have to explain how much hydrogen was present and for how long. Invoke clouds, and their altitude and thickness matter. Their distribution matters too. Invoke impacts and you get heat, but often with short clocks and violent consequences. The point is not that any one answer is impossible. The point is that ancient Mars refuses a free lunch. Every warming mechanism must be paid for with evidence and physics. A story that makes rivers easy may make atmosphere hard. A story that makes climate plausible may make long surface habitability harder. Two rocky planets, same star, different sizes and atmospheres, different interiors and fates. The time threshold may live inside that divergence. Earth had enough mass and internal activity. It had enough atmosphere and recycling to keep habitability broad and persistent. Mars may have had enough to start down the same road, but not enough to stay on it. And that takes us directly to the chemical fingerprint that the atmosphere should have left behind, if it solved the warmth problem for long enough. The molecular hydrogen hypothesis deserves more than a passing mention, because it shows how the climate debate is also a chemistry debate. Molecular hydrogen in an early Martian atmosphere could act as a greenhouse gas under certain pressure and temperature conditions. Some climate modeling work suggests that if Mars had enough hydrogen outgassing from volcanic sources or from water-rock reactions such as serpentinization, it could push the greenhouse beyond what carbon dioxide alone provides. The attractive feature of the hydrogen hypothesis is that it sidesteps some of the carbonate problem. If hydrogen rather than carbon dioxide was doing significant greenhouse work, the footprint left in the rock record would be different. Carbon is not in hydrogen. The mineral and atmospheric signatures diverge, but hydrogen also has a cost. It escapes from planetary atmospheres quickly, lighter atoms are more easily lost to space, and Mars's lower gravity makes this more severe. A steady supply of hydrogen from volcanism or water-rock reactions is needed to maintain the greenhouse effect over long intervals. Whether early Mars had the right outgassing rates, the right atmospheric pressures, and the right conditions to hold hydrogen in place long enough to matter is still being worked through, and this points to a larger issue. Mars's interior history is directly connected to its habitability history. A larger, more geologically active planet stays warm internally for longer. It outgasses more. It renews its atmosphere through volcanism. It drives hydrothermal systems through volcanic heat. Earth's plate tectonic activity recycles carbon through the mantle and returns it to the atmosphere, creating a long-term regulator. Mars lacks plate tectonics in the same way. Its carbon cycle, if it ever had one comparable to Earth's, was more limited. Once carbon was locked into minerals or lost to space, Mars had fewer mechanisms to replenish it, so the faint young sun problem is not only a solar problem, it's partly a Martian interior problem. A smaller planet cools faster, its magnetic field weakens, its volcanic activity declines, its ability to sustain an atmosphere against solar wind erosion diminishes. All of this happens more quickly than on Earth, and all of it affects how long warm surface conditions could persist. Mars also has something unusual about its rotation axis. Without a large stabilizing moon, Mars's axial tilt, its obliquity, varies chaotically over geological time. Earth's obliquity shifts within a narrow range, partly because the moon damps large variations. Mars has experienced obliquity swings from near zero to high angles over millions of years. High obliquity changes where sunlight falls, where ice forms, and how the atmosphere behaves. It can shift ice from one hemisphere to another. It can change seasonal water vapor. It can create conditions where surface ice melts in some settings, while other regions become colder. This adds another layer of complexity to the habitability question. Ancient Mars was not a static planet pointing the same direction at the Sun throughout its early history. It was tumbling slowly through a range of orientations. Each one changed where liquid water could exist, how long ice stayed put, and whether a habitable setting was stable enough to matter. A climate that supports a lake under one obliquity regime may not support it under another. A permafrost region that locks water in ice under one orientation may release that water when the tilt shifts. The biology question asks whether any setting had stability across those changes, and the obliquity record suggests that stability at the surface was harder to guarantee than a simple static picture implies. What does this mean for the valley networks and deltas we started with? It reinforces the interpretation that surface water may have been episodic in character. Not because Mars was always cold, but because its climate state was not constant. The planet may have moved in and out of favorable conditions as its obliquity shifted, its volcanic activity changed, and its atmosphere gradually thinned. And if surface conditions were episodic, the life question sharpens once more. Life needs not just the right conditions, but the right conditions persisting for long enough. A planet that oscillates through habitable and hostile states may offer episodes without providing continuity. Understanding the frequency, duration, and regularity of those episodes is part of what the climate debate is about. We are not choosing between a warm Mars and a cold Mars. We are asking how many useful windows Mars had, how long they stayed open, and how close together they were. Carbon dioxide is the intuitive greenhouse gas for early Mars. Imagine a thicker, ancient atmosphere wrapped around the planet, trapping more heat than the thin air Mars has today. Add enough carbon dioxide, perhaps with help from other gases, and surface water becomes easier to picture. Lakes last longer. Rivers make more sense. Then the rocks complicated. Carbon dioxide does not just sit in an atmosphere forever. In the presence of water and rock, carbon can become locked into carbonate minerals. On Earth, carbonates are part of a huge planetary exchange between air and water, rock and eventually life. Mars is not Earth, but the principle still holds. A long-lived, thick carbon dioxide atmosphere interacting with watery environments could leave mineral traces. Carbonates do exist on Mars. The problem is not simple absence. The problem is whether their abundance and distribution fit the simplest version of a dense, warm, long-lived greenhouse. Context matters too. In places like Gale, the evidence for ancient lake environments sits beside questions about why expected carbonate signatures are not stronger if the atmosphere was thick and stable for long periods. And that does not disprove warm Mars. It makes simple warm Mars harder. That distinction matters. The carbonate issue should not be turned into a courtroom verdict where one missing mineral solves the whole planet. Mars has a complex surface history. Carbonates can be buried or altered, they can form unevenly or be masked by later processes. Local chemistry matters, water chemistry matters, later alteration matters. The record we see is filtered through billions of years of change, but the issue still carries weight, because duration leaves chemistry behind. A brief warm pulse can melt ice and move water without giving the atmosphere and crust much time to equilibrate. A long, stable greenhouse should leave broader chemical consequences. If those consequences are muted or patchy, scientists have to adjust the story. The same is true when they conflict with the simplest models. Maybe carbon dioxide alone was not enough. Maybe other greenhouse gases helped. Molecular hydrogen under certain atmospheric conditions, for instance. Maybe clouds behaved in ways that changed the climate in unexpected directions. Maybe warming came in episodes, driven by impacts or volcanism. Maybe the surface was often cold while local settings stayed wet or protected underground. Each solution shifts the habitability question. If extra greenhouse gases helped sustain warmth for long intervals, Mars may have had broader windows. If warming depended on short-lived events, the windows narrow. If local settings solved habitability without global warmth, then Mars may have had important refuges, but not an easy planet-wide pathway. So the carbonate problem matters because it turns time into a mineral question. A warm atmosphere is not just a feeling in the air. The atmosphere becomes a chemical participant. It touches water. Water touches rock. Rock keeps some memory of the exchange. When the memory is incomplete or surprising, the climate story has to become more careful. Think of Gale Crater at a human scale. Curiosity is not just wandering across red dust. The rover is reading layers formed under ancient environmental conditions. Those layers record lakes, sediments, and minerals across geological time. Chemical change is written through them too. They can tell us what kind of water existed. They can also show how the environment shifted, but Gale does not hand us a single clean answer. It shows habitability in a defined setting, while also raising questions about the broader atmosphere that made that setting possible. And that tension is exactly what we need. A local lake can be habitable even if the global climate was not comfortably Earth-like. A planet can host serious environments without becoming a stable blue world, so we have to resist both extremes. We should not say the carbonate problem kills ancient warm Mars. It does not. We should not ignore it because the rivers look persuasive. We cannot. The whole point is that the river record and the climate record have to be made compatible with each other. Here's what that means for the life question. Chemistry is time's handwriting. A long atmosphere writes differently from a short pulse. A lake that persists writes differently from a flood. A groundwater system writes differently from a surface runoff event. When the writing is faint or inconsistent, the duration claim weakens. When it is strong and contextual, the duration claim strengthens, and so a warm greenhouse cannot be a magic wand. If someone argues Mars was warm for a long time, the next honest question is what that warmth did to the rocks. If the answer is complicated, the life window becomes complicated too. Look at what happens when we follow this constraint to its logical end. Maybe the deeper truth is that Mars was always struggling to hold the line. Warm enough here, wet enough then. Chemically promising in one basin, protected underground somewhere else. A planet making temporary agreements with habitability instead of signing a long contract. And that possibility fits the title question better. Not, did Mars ever become blue, but, did any version of Mars stay useful long enough? The carbonate problem does not answer that alone. It narrows the range of easy answers. It says a long-lived warm atmosphere should leave evidence we can test. It forces warm and wet models to work harder. It makes episodic, hybrid, and local pictures more important. And that leads into the central split in how scientists read the same ancient planet. One specific piece of the mineral record is worth examining directly, because it shows both the power of the carbonate argument and its complexity. Carbonate minerals have been found on Mars. The question is whether their distribution and abundance match what we would expect from a long-lived, warm, dense carbon dioxide atmosphere interacting with liquid water. The Comanche outcrop in Gusev crater, explored by the Spirit rover, provided some of the stronger early evidence for substantial carbonate formation. At Neely Fosse, orbital observations showed carbonate minerals in a large region of ancient terrain that also contains olivine and clay minerals. Both are important detections, but the context matters. Neely Fosse is a geologically complex region that shows evidence of multiple episodes of alteration. The carbonates there may record specific water-rock interactions in particular settings rather than a globally dominant carbonate-forming process. Gusev showed carbonates within a specific volcanic terrain with its own local chemical history. What would we expect if Mars had a dense, warm, long-lived carbon dioxide greenhouse with widespread surface water? We might expect carbonates to be more pervasive, more widespread geologically, more dominant relative to other alteration minerals across ancient terrain. The carbonate detections we have are real and significant, but they appear patchier than the simplest model would suggest. This does not prove warm Mars was impossible. It means the simple version of warm Mars, a dense CO2 atmosphere sustaining globally warm and wet surface conditions for hundreds of millions of years, faces chemical questions. Perhaps carbon was absorbed underground in ways that limit surface carbonate expression. Perhaps the atmosphere had lower pressure than some models assumed. Perhaps acidic conditions in later phases altered earlier carbonates into other minerals. Perhaps the timing was shorter than assumed. A mineralogical transition written in the Martian surface tells a story about changing chemistry over time. Orbital spectroscopy shows that the oldest ancient terrains are often clay-bearing. Somewhat younger surfaces often contain sulfate minerals. The youngest surfaces where alteration is visible show limited water-related chemistry. This sequence, clays to sulfates to minimal alteration, suggests that the character of water-rock interaction changed across Martian history. Clays typically form in near-neutral pH water, over relatively long durations. Sulfates can form in more acidic conditions in evaporating basins or in environments where volcanic sulfur dioxide played a larger role. The transition from clay-forming to sulfate-forming conditions may record a shift in how water interacted with the Martian surface. Changing atmospheric chemistry or volcanism may have driven it. Declining groundwater availability may have mattered too. This matters for the life question because different kinds of water are more or less friendly to life as we know it. Neutral to mildly alkaline waters with mineral nutrients are generally more hospitable than highly acidic or highly sulfurous waters. A transition from clay-forming to sulfate-forming conditions could record a changing habitability landscape, not just what was present, but what the conditions were like for chemistry, and the timeline of this transition is not pinned with precision. Did the shift happen over millions of years or hundreds of millions? Was it global or regional? Did some settings maintain clay-forming conditions longer than others? Answering those questions changes how much habitable time Mars accumulated in the more favorable range. So the carbonate problem is a broader chemical history problem. Mars preserves a mineral record that contains real information about ancient conditions. That record fits some models better than others, and the model that fits best shapes our understanding of how long the most habitable window stayed open. Here's the practical upshot. Climate models of ancient Mars are not theoretical exercises alone. They are forced to confront the mineral record, the escape record, and the volcanic record. The geomorphic record has to fit as well. A successful model has to explain rivers and the carbonate record. It also has to fit atmospheric history while remaining consistent with volcanic outgassing and solar evolution. The constraint is demanding, and those demands have been pushing the field toward hybrid pictures. Not a simple warm Mars, not a cold Mars with only random puddles. Something more complicated and more useful to test, which brings us to the central interpretive split in Mars science. Two ancient Marses hide inside the same planet. One is warm enough for rain and runoff, crater lakes, and a more connected water cycle, the Mars that makes valleys and deltas feel natural. Water moves across the surface because the climate allows it. Lakes persist because the atmosphere protects them. Habitable environments have room to last. The other Mars is colder. Ice dominates more often. Liquid water appears during episodes, after impacts or volcanic pulses, under favorable orbital conditions, or inside local systems where heat and water meet. And this Mars can still make rivers and lakes, but the water is less continuous. It arrives in windows that open and close. Both pictures are attempts to respect the same evidence. Warm and wet Mars starts from the landforms. Some valley networks look easier to understand if precipitation, runoff, or a broader hydrological cycle operated over meaningful intervals. Deltas and lakebeds feel less strained if basins filled and persisted. Widespread mineral alteration becomes easier if liquid water was a recurring part of the surface environment. For life, that version is tempting. A warmer planet gives chemistry time to operate across landscapes. Habitats might connect, lakes might last, groundwater might circulate. Organisms, if they began, would have more ways to persist and spread, but warm and wet Mars has to pay the climate bill. The faint young sun does not go away. Greenhouse mechanisms have to be strong enough. The atmospheric history has to be plausible. Mineral consequences have to make sense. Carbonates and escape rates become part of the argument. So do atmospheric pressure, clouds, and volcanic gases. Cold and icy Mars starts from the physics. Under a dimmer sun, a mostly frozen planet may be easier to maintain. Ice can sit on the surface or near it. Then special events create melting. An impact injects heat. Volcanism releases gases or warms local ground. Orbital changes alter where sunlight falls. Ice-covered lakes or groundwater systems may survive under protection even as the surface stays frigid. For geologists, this version can still produce water-shaped evidence. Meltwater can flow, lakes can form, sediments can move, minerals can alter. A planet does not need to be warm everywhere for liquid water to leave its marks. But the question for biology tightens. Were the melt events long enough? Did they recur in the same places? Did they connect chemistry or scatter it? Did the cold intervals preserve progress or reset it? Each of these questions has a different implication, and none has a clean answer yet. Picture a cold planet with brief thaws, a frozen cabin where someone lights a fire every few centuries. The walls show smoke marks, the floor shows footprints. Something happened there, again and again, but the cabin was never lived in continuously. The system never came alive as a home. That may be too harsh for Mars. Some windows could have lasted far longer than a simple analogy suggests. But the question of what kind of stability each window had remains genuinely open, and that is where hybrid pictures become attractive. Mars may not have been one simple climate state. It may have shifted through time. Early periods could have been wetter, later periods colder. Regional conditions could have mattered differently at different latitudes and elevations. Ice and groundwater, impacts and volcanism, and the atmosphere may have combined differently in different eras. A hybrid Mars is messy, but real planets are messy. The useful question is not which picture feels nicer. It's what each picture does to the continuity of habitability. Warm Mars offers continuity but must earn it physically. Cold Mars offers physical plausibility but must earn biological relevance. Hybrid Mars accepts complexity but must avoid becoming unfalsifiable fog that hides the question instead of answering it. Here's a concrete test. Does each model give Mars productive continuity? A warm model must show how warmth was sustained and recorded. A cold model must show how brief water episodes became useful rather than merely scenic. A local model must show how protected environments avoided isolation. The shape of the planet we choose has direct consequences for whether life was ever possible. Look at what the same river channel means under each climate. In a warm world, it may be part of a larger hydrological network carrying chemistry across regions. In a cold world, it may be the result of transient melt from one event. In a hybrid world, it may record one phase of a changing planet. The shape on the ground is not enough. The climate history gives it biological weight, and so Mars can feel so close and so distant at the same time. Close because we can see the forms water left behind. Distant because the conditions that made those forms may have been nothing like the Earth-like scene we imagine. A delta on Earth sits inside a living water cycle. A Martian delta may have formed in a crater during a limited era, under conditions that later vanished completely. If warm and wet Mars is right for long enough periods, then the life question becomes more open. Not settled, but genuinely more open. If cold and icy Mars with transient melting dominates, then the strongest possibilities may shift away from broad surface habitability and toward special places where time was protected. Those places are where we go next. Because even if the whole planet could not stay warm, life never required the whole planet. It required somewhere. The geological timescale of Mars adds another layer of constraint that the two-model debate cannot ignore. Mars is divided into three broad geological eras based on crater counting and surface alteration history. The Noachian is the oldest, corresponding roughly to the first billion years or more of Mars history. It was the era of the most intense valley network formation, the most widespread clay mineral alteration, and the heaviest cratering. The Hesperian follows. It becomes associated with large volcanic floods, different mineral alteration chemistry, and evidence of declining surface water activity. The Amazonian is the youngest and largely cold, dry, and geologically quiet by comparison. The valley network story clusters strongly in the Noachian and early Hesperian. That tells us the conditions that allowed rivers and lakes to form were strongest early and then declined. What caused the decline is a crucial part of the habitability story. Was it loss of atmosphere through solar wind erosion, internal cooling reducing volcanism and reducing atmospheric replenishment, an impact-driven loss event, a combination that tipped the system past some threshold? Under warm and wet models, the end of the Nuea corresponds to the loss of the conditions that made broad surface habitability possible. Under cold and icy models, the valley networks record the best melt events of an episodic ice world, and their declining frequency records changing drivers rather than a lost ocean. For life, these two readings suggest very different amounts of available time. A warm and wet Noachian Mars could have maintained surface habitats for hundreds of millions of years during the period when valley networks were active. A cold and icy Mars with episodic melts may have offered surface habitats measured in shorter pulses, each one impressive geologically but brief biologically. Here's the honest position. Neither model has been ruled out by the current evidence. Both have advocates among planetary scientists with deep expertise in the relevant data, and both are actively developed using better atmospheric models, better constraints from mineral data, and more detailed geologic mapping. What we can say is that the debate itself has implications for the life question. If warm and wet Mars held broad surface habitability for a significant fraction of its early history, even if that history eventually ended badly, then the question is whether life had time to begin during that era. If cold and icy Mars is closer to reality, then the question shifts toward the local windows, the specific places where protection and energy and water met outside the surface climate. Both models may also describe real phases of the same planet. Early Mars under the heaviest volcanic outgassing might have been warmer. Mars as volcanism declined might have cooled. The transition between those states might be recorded in the valley networks, not just how many there are, but when they formed and in what sequence. Craters formed on Mars have been used to estimate when certain terrains were last modified, and the ages of valley networks are an active research area. Better age constraints would tell us whether the rivers flowed continuously over a long early period or formed in episodic bursts across a larger span. The chaos of Mars's early bombardment also complicates the picture. The planet received enormous impactors early in its history. Some could have created temporary warming through impact heating or volatile injection. Others could have driven local hydrothermal systems. These events could produce hydrological activity that leaves a valley network or delta without requiring the same sustained climate a warm and wet scenario demands. So even within cold and icy Mars there is a spectrum. Brief impact-driven melts are one end, longer impact-driven hydrothermal systems are another. Regional climate variations driven by obliquity or volcanic activity are another. The common thread is that duration within any warm event becomes the critical variable, and here warm and wet Mars has an advantage. If broad habitability lasted for a long period, the system had more chances to accumulate productive chemistry. Cold and icy Mars must find that productivity within a harder constraint, brief windows that have to do more work per unit time. Both pictures are Mars. One of them is closer to the truth. The geological record, the mineral record, and the climate models are slowly forcing us toward a better answer. But the answer will change how we read the life question in practical ways. So we have to take both seriously and let neither become a story we tell ourselves for comfort. A planet does not need every surface to be habitable. Earth itself teaches that. Life clusters around vents, sediments, and soils. It also appears at lakes, ice margins, and deep rock boundaries. Some environments are harsh. some are dark, some are temporary, some are sealed away from the surface entirely. Habitability can be local, and that matters enormously for Mars. If early Mars struggled to keep a warm global climate, we should look for protected settings. Crater lakes, groundwater systems, and hydrothermal environments are the obvious candidates. Impact-heated basins or volcanic regions may have mattered too. Local windows make Mars more hopeful. They also make the problem sharper. Think about a crater lake. A basin like Gale or Jezero can collect water and sediment. It can build layers. It can preserve minerals and perhaps organic chemistry. If the lake lasts and refills, or if it interacts with groundwater, it becomes more than a puddle. It becomes a record of an environment with its own history. But a crater lake is still a place. Its biological meaning depends on duration and chemistry, energy and connection. A lake that forms briefly after an impact may be scientifically useful, but too short-lived for origin chemistry to progress. A longer lake fed by groundwater may be more promising. A lake that repeatedly dries and refills may either concentrate useful chemistry or punish it with destructive resets. The difference between those outcomes is what we cannot always tell from a rock. Now consider hydrothermal systems. Water moving through hot rock can pick up minerals, create chemical gradients, and supply energy. On Earth, hydrothermal environments are central to many ideas about early life. Mars had volcanism and large impacts. It had water-rock reactions confirmed at multiple sites. Subsurface hydrothermal habitats are not fantasy. They may even solve some of the surface problems. Below the ground, water can be shielded from radiation. Temperature swings are less violent. Rock can provide chemical energy through processes like serpentinization, where iron-rich minerals react with water to release hydrogen. A surface that is cold and hostile may sit above a deeper environment where water and chemistry keep working quietly for a long time. But the subsurface has its own questions. How accessible were the ingredients to each other? Did fluids circulate through useful pathways? Were there compartments, gradients, and mineral surfaces in the right arrangements? And if life began underground, how would we ever know? The most important Martian environment may be the one least visible in the surface record, so local habitability is not automatically easy. Impact heat creates another kind of window. A large impact can melt ice and heat groundwater. It can create hydrothermal circulation, temporarily transforming a region. For a cold planet, impacts may be the moments when water becomes liquid and chemistry accelerates dramatically. But impacts are violent clocks. They start hot, then cool. Their habitable aftermath may last for a time, perhaps thousands to hundreds of thousands of years for the largest events, but not indefinitely. The question becomes whether that time was long enough, and whether similar windows repeated in ways that helped rather than erased progress. Volcanism offers a slower possibility. Volcanic gases can affect climate. Heat can melt ice. Hydrothermal systems can form around magmatic intrusions. Chemical energy can arise where water meets fresh rock. Mars had enormous volcanic provinces. Tharsis represents billions of years of volcanic activity, and its interior history matters enormously for the habitability story. Again, the key is overlap. Heat alone is not enough. Water and organics are not enough either. Even shelter needs the rest of the system. The window matters when these pieces meet and stay together long enough for chemistry to accumulate. Groundwater may be the most quietly important candidate of all. Surface Mars could freeze, dry, and lose atmosphere, while subsurface water remained protected in certain places. Groundwater can connect basins differently from surface rivers. It can move through rock and alter minerals. It can carry dissolved chemicals, while shielding environments from surface radiation and oxidants. If Mars had long-lived groundwater systems, then the surface may be only the visible edge of the habitability story. But groundwater is hard to read from orbit. It leaves mineral traces, cementation patterns, and alteration halos. Layered deposits can help, but the evidence is indirect. A rover can examine local signs, but reconstructing the length and connectivity of ancient subsurface habitats is difficult work that requires multiple lines of evidence. Here's the pattern with every local window. The possibility is real, the proof is hard, and the duration is always the hinge. A local habitat can be more important than a global climate if it stays open long enough. A small protected environment can matter more than a huge surface flood if it preserves chemistry through time. A buried water rock system can be more biologically serious than a spectacular valley carved by brief meltwater. Scale can mislead us. Mars may have had large-looking water features that were biologically brief and small hidden settings that were biologically deeper. The dramatic landscape is not always the most important habitat. The best place for life might not be the place that photographs well. Look at the edges of these environments. On Earth, some of the most interesting habitats are not broad, comfortable landscapes. They are boundaries. Hot and cold, wet and dry, rock and water. Life often exploits boundaries because boundaries hold energy and contrast. Mars had boundaries in abundance. The question is whether they were stable enough and gentle enough for prebiotic progress, rather than too violent to let chemistry accumulate. A hydrothermal fracture beneath ice might have water and heat. It might have chemical energy, but little sunlight. A shallow evaporating lake might have concentration and mineral cycles, but growing salinity or acidity. A groundwater system might have protection and duration, but limited access to fresh organic material or atmospheric inputs. An impact-heated lake might have sudden warmth, but a cooling deadline and a traumatized starting chemistry. Each setting gives and takes, and still, local windows create a final problem worth naming. If each promising place is isolated, does Mars become a planet of near misses? One crater gets water, another gets heat. A subsurface pocket gets protection, a different basin gets organics. Across billions of years, the list looks rich. In real time, the pieces may never have met in the same place, so local windows do not remove the time problem. They focus it. Could any one place on Mars keep water, chemistry, and energy together long enough for a chemical pathway to deepen? Could shelter last with them? Could that place survive the planet's larger collapse? Could it connect to other habitats? Or did it remain a sealed opportunity? If global climate was not enough, local windows are the strongest next answer. But to judge them, we have to understand what the ingredients need to do, and why a list of them is still not a recipe. Serpentinization deserves a careful look here, because it is one of the more compelling mechanisms for sustaining a habitable environment on a planet that is cooling and drying at the surface. The serpentinization happens when water reacts with iron and magnesium-bearing silicate rocks. Olivine and pyroxene are the primary minerals. Under the right conditions, the reaction produces serpentine minerals, magnetite, and molecular hydrogen. The reaction is exothermic. It generates heat, it generates hydrogen, which can be used as an energy source by certain kinds of microbial life. It does not require sunlight. It does not require a warm atmosphere. On Earth, serpentinization occurs in ocean floors and continental settings, where water encounters fresh mafic or ultramafic rock. Particular ecosystems in deep ocean environments and within terrestrial mines have been found to live on hydrogen produced by serpentinization, completely disconnected from photosynthesis. These communities are not abundant, but they demonstrate that life can find a foothold in chemical energy generated by rock-water reactions in the dark. Mars has abundant olivine-bearing terrain. The Nili Fosse region is one example. Olivine, serpentine minerals, and carbonate minerals have been detected close together there. That's a signature potentially consistent with ancient serpentinization. Globally, ancient Mars had the kind of mafic and ultramafic crust that could support this kind of water rock chemistry, and serpentinization can outlast surface water by a significant margin. A planet can lose its lakes and rivers to cold and dry conditions while its subsurface rock continues to react slowly with groundwater. Reaction rates slow as the temperature drops and the most reactive rock surfaces are consumed. But in a geologically young crust with fresh fractured rock and access to groundwater, serpentinization can persist for extended periods. This makes it a candidate for bridging Mars's timeline problem. If surface windows closed earlier, subsurface serpentinization could continue generating chemical energy and maintaining liquid water in isolated pockets, shielded from radiation and temperature extremes. Whether any such environment persisted long enough to matter for life is another question. But the mechanism is real, documented on Earth, and physically plausible on early Mars. The Eridania region in the southern highlands is worth mentioning specifically. Based on orbital data, some researchers have proposed that this basin may have once held a large ancient sea. It may have been deep and perhaps fed by groundwater and hydrothermal activity rather than simple surface runoff. If that interpretation is correct, the environment could have had water depth, mineral variety, and heat sources. It may also have had enough protection to sustain complex chemistry for an extended period. Eridania is one of the more detailed proposals for a long-duration local window on Mars. Eridania is not proven. The interpretation fits certain spectral and topographic data, and it remains consistent with some climate models. But it illustrates how the local window story can scale up. A single crater lake is one kind of window. A large ancient sea fed by hydrothermal systems could be something more substantial, not quite the global ocean some popular Mars stories imply, but a real large-scale environment with its own chemical history. The timing of impact hydrothermal systems relative to the planet's overall cooling is also relevant. Large impacts were more frequent early in Mars history. Each large impact could create a hydrothermal system lasting from thousands to hundreds of thousands of years, depending on the size of the impactor and the local geology. The overlap of those systems across the Noachian era means some part of the planet may have been hydrothermally active almost continuously. Not one system at a time, many systems overlapping, each adding to the overall hydrothermal flux. If we imagine early Noachian Mars with frequent large impacts and overlapping hydrothermal systems, the picture changes. Widespread volcanism adds another layer. Some greenhouse warming and available water may have joined that activity. The result is not a barren cold world, but a violently active world with chemical possibilities and disruptions. Life, if it tried to begin in an impact-driven hydrothermal system, would have found energy and water. It might also have found that its home was eventually destroyed by the next large impact. Resilience would have been part of the test, and that resilience would have been possible only if chemistry had advanced far enough to persist through disruption, which requires not just the right environment, but the right environment for long enough before disruption. The local window problem is ultimately a timing problem dressed in geography. The phrase "ingredients for life" sounds more complete than it is. It gives us a list: water, carbon, and hydrogen. Then the list widens into the rest of life's chemistry. Add organics and salts. Add energy, mineral surfaces, and some protection from radiation. Put them together on one planet, and the situation starts to feel promising. But a list is not a process. A kitchen can contain flour, water, and yeast. It can also contain salt, heat, and time. That does not mean bread is forming somewhere in the room. The ingredients have to meet in a certain order. Conditions have to change in useful ways. Too much heat ruins the dough. Too much water disperses it. No time and nothing develops. Origin chemistry is vastly more complicated than bread, but the lesson is plain enough. Arrangement matters. Mars may have had many of the right materials. Curiosity's detection of organic molecules in Gale matters because carbon-bearing chemistry survived in ancient rocks over billions of years. Minerals formed in water matter because surfaces can influence chemistry and preservation. Redox gradients matter because life uses chemical differences for energy. Salts and shifting water chemistry shape concentration and stability, but every one of those clues has to be translated into a working environment. Did organics form locally, arrive from space, or get altered after deposition? Each origin implies different chemistry and a different preservation story. Were they concentrated or scattered? Concentration matters because productive reactions require molecules to meet. Were they near energy sources, and were they buried quickly enough to avoid destruction at the surface? Did water chemistry preserve them or expose them to the same oxidants that Mars generates in abundance near its surface? Did mineral surfaces help organize reactions, or only record the alteration that happened after the interesting chemistry had already stopped? Here's where the difference between present and productive becomes everything. Water can help chemistry by dissolving and moving molecules. It can also dilute them until reactions become unlikely. Drying can concentrate molecules. It can also leave them exposed to radiation and oxidation. Ultraviolet radiation can drive some reactions. It can also break organics apart. Oxidants can create energy gradients. They can also damage fragile compounds before they accumulate. Habitability lives in those trade-offs, and that is exactly why a simple checklist can mislead. If we ask only whether Mars had carbon, water, and energy somewhere, the answer can sound encouraging. If we ask whether those pieces formed a sustained reaction network in a protected setting, the answer becomes genuinely uncertain. Think about what Origin of Life research asks for. Origin of Life research proposes competing ideas. Surface pools with wet-dry cycles are one. Hydrothermal vents and mineral surfaces are others. Ice chemistry, metabolism-first pathways, and RNA world chemistry add more possibilities. Mars does not have to choose our favorite model, but each model asks Mars for different specific conditions. A shoreline model wants wetting and drying cycles close to mineral surfaces. A vent model wants sustained water rock energy gradients at manageable temperatures. An ice model may need concentration in brine pockets and repeated freeze-thaw transitions. Other models ask for their own narrow conditions. Each pathway has its own set of environmental requirements. Mars may favor some pathways and punish others. A cold planet with intermittent melting might be bad for continuous surface ponds, but good for certain concentration mechanisms. A hydrothermal Mars might support energy gradients, but bury the most important chemistry out of reach. An evaporating lake might concentrate salts and organics, but become too harsh for the next step. A clay-rich deposit might preserve molecules well, but not be where they first formed. So the environment has to do more than look friendly. It has to perform. Performance means molecules are not merely present. They are moved, concentrated, and altered. Then they have to be protected and carried into new states. The system has to resist total erasure. If each thaw starts fresh, the chemical story remains shallow. If each cycle leaves something useful behind, time begins to accumulate, and that is why duration and chemistry cannot be separated. A short event can matter if it plugs into a longer sequence. A long environment can fail if it never concentrates or energizes the right chemistry. A drying shoreline may be more productive than a deep, stable lake for some pathways. A protected subsurface gradient may be more useful than an open surface pool for others. So when we ask how much time Mars needed, we are asking several distinct questions. Enough time for a lake to exist? One question with one set of answers. Enough time for water-rock reactions to generate chemical energy? A different question with different requirements. Enough time for organics to accumulate? Different again. Enough time for cycles to repeat without completely resetting the starting chemistry? Different still. The phrase enough time covers a range of specific demands that are only loosely related, and here is where preservation complicates everything further. The places that preserve organics best may not be the places where origin chemistry was most active. Fine sediments can bury and protect signals, clays can hold chemical traces, quiet lakebeds can preserve layers. But high-energy chemical environments may be harder to preserve cleanly, or may destroy their own most interesting evidence in the process of generating it. So a rover finding preserved organics in an ancient sedimentary rock is thrilling. It tells us something survived. It does not automatically tell us that the environment where it was preserved was the place where life could have begun. Those may be different locations. Chemistry, distance, or deep time may separate them. Again, Mars gives us possibility, then demands restraint. The strongest version of the case is not Mars had the ingredients, so life was likely. The strongest version is that Mars had many ingredients and many plausible settings, but the unanswered question is whether they were arranged into productive sequences before the planet's windows closed. And that phrasing is more useful than a simple yes, because it puts Mars exactly on the boundary, not empty, not settled. A world with enough evidence to make the question real, and enough missing continuity to keep it open. Once ingredients become sequences, the next problem appears naturally. Could those sequences survive the planet's own history of disruption? Phosphorus availability deserves special attention because it highlights how ingredient checklists can mislead even when they are incomplete rather than wrong. Phosphorus is essential for the chemistry of life as we know it. DNA, RNA, and ATP all require phosphate. The structural chemistry of cell membranes involves phosphate groups. Origin of life pathways that involve RNA need phosphate available in solution. On Earth, the source and availability of dissolved phosphate in early ocean or pond environments is an ongoing research question. In seawater, phosphate concentrations are often low because organisms and minerals compete to use it. This has prompted research into concentrated phosphate settings. Evaporite environments and alkaline lakes are two candidates. So are settings where phosphate minerals dissolve into solution rather than precipitating quickly out of it. Mars has phosphate minerals. Curiosity detected them. In some ancient aqueous settings, those minerals may have dissolved into water. But the key is whether they were in solution at the right concentrations, in the right conditions, without being immediately precipitated or locked away by competing ions. Calcium, iron, and magnesium are abundant in Mars rocks. Under some conditions, they can bond with phosphate and remove it from solution. Highly acidic or highly alkaline water may dissolve phosphate minerals differently. The specific pH, ion composition, and temperature of any given ancient Martian water body would determine how much dissolved phosphate was available. And we do not know those parameters with confidence for most candidate ancient environments. We should not dismiss Mars because of that. We should recognize that a checklist of elements begins the inquiry. It does not end it. The same logic applies to the organic molecules Curiosity detected. The presence of organic carbon in ancient Gale rocks is genuinely important. It confirms that carbon chemistry can survive in the Martian subsurface for billions of years, which is not trivial. It also gives researchers chemical targets to study. But organic molecules are not a single class of compound with a single meaning. Carbon-bearing molecules span a range from simple to complex, from biologically meaningful to completely non-biological. The question is not whether organics are present, but what kind and in what context. We need to know how they formed and what protected them. A simple aromatic hydrocarbon delivered by a meteorite tells a very different story than a lipid or a nucleotide precursor formed within a watery Martian environment. Both are organic molecules. Their implications differ enormously. Think about a pantry full of cooking ingredients: sugar and flour, salt and spices, water, oil and yeast. Everything a baker could need is there. Now ask, has anything been baked? The pantry itself doesn't tell you. You need to know whether the ingredients were measured and combined in the right order, subjected to the right conditions, and allowed the right amount of time. The pantry could have been stocked and then abandoned. The oven might never have been lit. Mars may have stocked a very interesting pantry in several ancient environments. Whether any of those pantries led to baking is not answered by listing their contents. Whether the conditions that favor preservation are the same as those that favor productive chemistry is its own question. A quiet, deep lake can bury and protect organic material very effectively. But a deep, quiet lake may also dilute chemistry below the concentration needed for interesting reactions. The best preserver is not always the best reactor, and the best reactor may be worse at preservation. A shoreline, a hydrothermal vent, or a concentrated brine can do chemistry while leaving a weaker archive. The history we can read and the history where chemistry was most active may not be the same history. So a rover finding preserved organics in ancient sediment is important for confirming Mars had a chemically interesting past. But it does not automatically mean the location was a cradle for life, nor does failing to find organics in a given rock mean nothing of interest happened there. The molecular evidence is partial by nature, and reading it honestly requires understanding both what it shows and what it cannot show. These limitations are not failures of the science. They are the current frontier of the science. Every mission that constrains the chemistry, the context, and the timing of ancient Martian environments moves the answer forward. Not quickly, but durably. And the hardest part of the story is not finding the right ingredients. The real challenge is determining whether they were ever arranged into something more than a list. A single habitable place can matter, but a biosphere asks for persistence. If life begins in one pool or lake, one vent or protected pocket, it still has to survive the closing of that first window. It has to endure change. It may need to spread or retreat, adapt or hide. Even a very simple biological system is more than a spark. It becomes a spark that keeps finding fuel. And on Mars, this is where scattered habitability becomes a problem. The planet may have had many promising environments. Valley networks in one region, a crater lake in another, groundwater somewhere else. Other clues appear as hydrothermal activity, mineral alteration, or organic preservation. Each one can be real and important in isolation, but if they were separated by too much space or too much time, the planet may have been rich in clues and poor in continuity. Environmental reset makes that worse. Imagine a city where lights turn on one building at a time, with centuries of darkness between them. From a far future satellite image, you might find evidence of electricity all over the city. Wires here, burned lamps there, power stations in several districts. But no one ever lived in an illuminated city. The system never came alive as a network. Mars may have had that kind of problem. Valley networks suggest some degree of integrated flow in places. Water did not only appear as isolated drops, it carved connected landscapes. That supports the idea that early Mars sometimes had broader hydrological activity. If rivers and basins were linked, then chemistry and sediment could move across regions, and habitats could influence one another. But the strength of that connection depends on the climate history we have been exploring. Under warm and wet conditions, networks may reflect a sustained surface water cycle. Under cold and icy conditions, they may record repeated melt events, dramatic but separated by long frozen gaps. The meaning shifts depending on which model we are working within. Connection across space is only half the issue. Connection across time may matter even more. If a lake exists for a while and disappears, the rock record says Mars had a lake. If another forms millions of years later in a different basin, the record says Mars had lakes. But biology would ask whether any chemical or biological progress could bridge the gap. Without a bridge, Each window is an isolated experiment that starts from scratch. Some bridges might have existed underground. Groundwater can connect places that surface maps separate. Fluids can move through fractures and porous rock. Chemical energy can be generated where water meets fresh minerals. Subsurface environments can be shielded from radiation and surface temperature swings. And that possibility is powerful, but it also hides the evidence. A surface rover can inspect accessible rocks. Orbiters can map minerals and landforms. But ancient subsurface networks are harder to reconstruct. Their traces may be indirect. Veins and alteration halos, cemented sediments, geochemical patterns exposed by erosion. The habitat may have been deeper than the record we can easily read. So the question becomes difficult in the exact place it becomes most interesting. Surface windows may be visible but brief. Subsurface windows may be longer but hidden. Lakes may preserve beautiful records, but not connect across time. Groundwater may connect but not reveal itself clearly. Impact systems may create energy but fade. Volcanic systems may last longer but be patchy and isolated. Mars never gives us the whole answer in one place. And this matters for the life question because origin and persistence are related but not identical. A planet might create life once and then kill it quickly. It might create many almost life chemical systems that never cross the threshold. It might support life underground while the surface becomes sterile. It might preserve traces only in rare sediments or erase them before we arrive. Now think about what survivable transitions mean. Could a lake drying out push chemistry into a new productive state? In some pathways, drying concentrates molecules and enables reactions that liquid water makes unlikely. Could a freezing interval preserve compounds until the next thaw? In cold environments, some biosignatures and organic structures can be shielded. Could groundwater carry energy and ingredients onward? In a connected subsurface network, maybe. Could a local system migrate as conditions changed across geological time? That requires both mobility and survival during transport. The answers differ by location, era, and what kind of chemistry we mean. But the pattern is consistent. Transitions are dangerous, and every closing window is a test. Look at the timing of Mars's decline. As the atmosphere thinned and the surface became harsher over hundreds of millions of years, surface habitats would have become harder to maintain. If life had already begun and found refuge underground, it might persist invisibly. If life had not yet begun, the closing surface windows could remove key origin pathways before subsurface settings alone could finish the job, and that possibility gives the phrase "too brief" its real meaning. It does not mean every wet event was short. It means the sequence from promising chemistry to persistent biology may have needed bridges Mars did not consistently provide, so one rover cannot finish this question. But one rover can change it. Gale showed that at least one ancient Martian environment was not a cartoon puddle. It was a serious and layered, mineral-rich and chemically complex system that persisted. Jezero may show whether a deltaic lake preserved the kinds of samples that can test habitability in greater detail. Each local story becomes a tile in a larger mosaic of windows. But before we can read that mosaic, we have to reckon with a harder problem. Mars does not show us ancient environments directly. It shows us what the rocks still remember. The broader context of Mars's geological history adds another dimension to the broken windows problem. The Noachian ended with a transition to the Hesperian, a transition that was not a clean calendar date, but a gradual and complex shift in how the planet operated. During the Hesperian, large volcanic floods called outflow channels scoured the terrain on a massive scale. These outflows were enormous. They could release staggering volumes of water from the subsurface onto the surface in geologically brief events. The channels they carved are visible today as some of the most dramatic large-scale features on Mars. Outflow channels are interesting from a habitability standpoint because they release subsurface water into surface environments. If that water was warm, or if it entered basins and persisted for significant periods, it could have created temporary lake or sea environments. The crease region, where several outflow channels terminate, may have received repeated pulses of water. But outflow channel floods are not subtle chemistry events. They are violent, fast, and potentially cold. Water might release suddenly from a subsurface aquifer. It might cross a frozen surface and enter a cold basin. The energy budget for sustaining liquid water there depends on conditions we can only reconstruct partially. A large flood can create a temporary lake. Whether that lake stayed liquid, stayed chemically hospitable, and remained undisturbed long enough to matter for prebiotic chemistry is a very different question. Hesperian volcanism also changed the chemistry of water-rock interactions. Volcanic sulfur dioxide, released in large amounts during major eruptions, reacts with water to form sulfuric acid. This could drive aqueous environments toward acidity. The transition from clay mineral-dominated terrain to sulfate-dominated terrain in Mars's mineral record may partly record the effect of Hesperian volcanic acidification on surface waters. Acidic conditions are not automatically hostile to life. Some microorganisms on Earth thrive in highly acidic environments. But the transition from the clay-forming conditions of the Noachian to the more sulfate-forming conditions of the Hesperian may record a change in the character of habitability. A neutral pH, clay-forming early Mars is often described as more broadly friendly. A sulfate-forming, more acidic Mars may have been more selective. Some settings remained hospitable, others became hostile. If biology had started in a Noachian setting and needed to persist through the Hesperian transition, it would have faced changing chemical conditions at a planetary scale. Whether that represents a filter or a challenge depends entirely on how far chemistry had progressed and how well organisms, or proto-life chemistry, could adapt or retreat to protected settings, and the transition from Hesperian to Amazonian represents another major change. As Mars lost more of its atmosphere over time, surface radiation increased. Oxidants were produced by ultraviolet light interacting with the thin atmosphere and surface materials. The surface became increasingly hostile to organic preservation. Any life in the last few 100 million years of Mars history would have been confined to subsurface settings, shielded from the increasingly harsh surface environment. This timeline puts a kind of deadline on the surface habitability story. Even if life began somewhere in the Noachian or early Hesperian, it would have needed to find protection before the surface conditions made persistence nearly impossible. Whether any biological system or any self-sustaining chemistry could have survived that transition is a central question for Mars astrobiology that has no clear answer. So the broken windows are not just spatial, they are temporal. Each era closed some possibilities and opened others. Noachian Mars may have been the best window for broad surface habitability. Hesperian Mars may have offered specific windows in a harsher environment. Outflow channels, volcanic hydrothermal systems, and remaining groundwater are the main candidates. Amazonian Mars is largely closed at the surface. Where are we now in that history? Deep in the Amazonian, the surface Mars we see today is not a good guide to the early Mars where habitability was most plausible. We are arriving billions of years after the most interesting chapters, reading them in the rocks as carefully as we can. Whether any chapter contained what we are looking for is still being read. Mars is not preserved equally. That sounds obvious, but it changes everything. The ancient planet that may have held lakes and groundwater no longer exists as a living set of environments. Its hydrothermal systems, organics, and protected sediments survive only as traces. We do not sample wet shorelines. We sample rocks. We do not watch rivers flow. We map channels. We do not collect fresh lake mud. We drill ancient deposits altered by billions of years of chemistry, radiation, and erosion. The record is filtered. Some environments preserve well. Quiet sediments can bury fine material. Clays can protect chemical traces. Layered rocks can record environmental sequence. Deltas can trap particles delivered by rivers. Lakebeds can keep a history of changing water and chemistry across thousands to millions of years. Other environments may matter for life but preserve poorly. High energy streams erode. Hydrothermal systems alter their own rocks chemically over time. Surface organics are vulnerable to radiation and oxidants. Shallow deposits can be stripped away by wind and impact. Burial can hide the best layers from our instruments, while exposure can degrade the most fragile signals, so absence is hard to interpret. If we do not find a biosignature in one place, did life never exist there? Did the environment fail to support it? Did the biosignature form and then vanish through alteration? Did we sample the wrong layer? Did the right signal survive but remain below detection limits? Did later chemistry scramble it? Those are different answers, and they can look the same in a failed detection. Here's why preservation bias is not an excuse for wishful thinking. It is part of the actual science. Mars may have had habitats that left little record. It may also have preserved beautiful water records in places that were never biologically productive. A good archive is not always a good birthplace. A good birthplace is not always a good archive. Jezero was chosen partly because deltas and lake sediments can preserve signs of ancient environments and possibly biosignatures. The choice is rational, grounded in decades of study. Fine-grained sediments, mineral contexts, and layered deposits give scientists a better chance of reading old conditions. But even Jezero is not the whole planet. A delta is a receiving system. It collects material from a watershed and deposits it in a basin. That can be excellent for preservation. It can also mix sources. A signal in a delta may have come from somewhere upstream. A missing signal may reflect chemistry or erosion, sampling limits or preservation, rather than the absence of life. Context does not guarantee answers. It makes the answers more meaningful. Gale offers another kind of archive. Curiosity has read sedimentary layers showing changing environments over time. That sequence helps scientists reconstruct habitability across eras. But Gale is also one crater, with its own history, chemistry, and burial. Its own erosion and exposure. It can reveal a serious habitable setting without deciding the whole planet's story, and so three questions must always stay separate. Did a habitat exist? Could it preserve evidence? Have we sampled the right material with the right tools? A yes to the first does not guarantee a yes to the second. A yes to the second does not guarantee a yes to the third. A no from our current instruments may be a statement about limits, not ancient reality. Time enters here too. Longer-lived habitats may leave thicker records, richer chemistry, and more complex sequences. Repeated wetting can build layers and mineral sequences. Persistent groundwater can alter rock over extended periods. A stable lake can accumulate sediment that tells a longer story, but long duration can also complicate preservation. Later water can overprint earlier chemistry. Burial can heat and alter material. Erosion can remove the crucial interval. Look at what that means for biosignature searches. A convincing signal must be difficult to explain without biology and consistent with its geologic context. Shapes can mislead. Chemistry can be ambiguous. Minerals can mimic biological patterns. Other signals can be altered or non-biological. Context is what separates an intriguing signal from a credible claim. So the search often proceeds by narrowing environments first. Before asking whether a rock preserves life, Scientists ask whether it records a setting where life could have existed. They ask whether preservation was plausible. Then they ask whether later processes damaged the record. That does not guarantee success, but it prevents the search from becoming random or wishful. Mars's old rocks are valuable because the planet lacks Earth's plate tectonic recycling in the same way. Ancient terrains can remain exposed for immense spans. That gives Mars an unusually clear archive of early planetary history. But exposure is also damage. The very surface that preserves ancient landforms can degrade delicate chemistry, so Mars is both generous and cruel. It keeps the big shapes. It may erase the small signals. It preserves the question at landscape scale while making the answer hard at molecular scale. And there is one practical implication. The exposed skin of Mars is not the same as the protected interior of a rock. Radiation and oxidants work from the outside inward. By opening a rock, even shallowly, through drilling and abrasion, a rover can see material that has been shielded from the worst surface damage. The small act has large meaning. Beneath the altered surface may be a better memory of the ancient environment. Not perfect, not guaranteed, but closer to the window we are trying to understand. And that brings us to the missions that are doing this work most carefully. One specific challenge in reading the rock record deserves attention because it touches the practical center of the biosignature search. Perchlorate. Mars's surface and near surface contain perchlorate salts, reactive oxidizing compounds detected by several landers and inferred from orbital data. On Earth, perchlorate exists, but is not typically found in concentrations that would overwhelm organic chemistry at the surface. On Mars, perchlorate appears to be widespread in the surface regolith. Perchlorate matters for the organic record because heating perchlorate-bearing samples can combust organic material. When the Viking landers tested Martian soil in the 1970s, they heated samples and detected chlorinated hydrocarbons. Those molecules could, in principle, be combustion products of organic material reacting with perchlorate. At the time, Viking's organic analysis was interpreted as mostly negative for organics. Decades later, scientists revisited those results in light of perchlorate, and some concluded that Viking may have destroyed organic material in the process of testing for it. Curiosity, using more sophisticated instruments, was able to detect ancient organics in drilled rock samples at Gale, despite perchlorate. The key was reaching deep enough into rock that the surface chemistry had less influence, and using careful analytical approaches. But the perchlorate issue illustrates something important. The apparent absence of organics may sometimes reflect chemistry we introduced through our instruments, or chemistry that was already working on the surface, rather than a true absence of ancient organic material. Drilling and subsurface access matter so much for this reason. The surface of Mars is a poor archive of ancient organic material. Ultraviolet radiation, cosmic rays, and reactive chemistry all work against preservation. Even a few centimeters below the surface, radiation damage decreases. Deeper still, the ancient chemistry may be better preserved. Scientists estimate that going a meter or more below the surface could dramatically improve the chances of finding organics that have not been destroyed by surface processes. Perseverance carries CROG, a Raman and fluorescence spectrometer that can detect aromatic organic compounds at high sensitivity. It can characterize organic molecules in place in rock without heating them. That capability is significant. But even CROG's reach into rock is shallow. The preserved organic record of Mars, if it exists in abundance, likely lives deeper than current surface rovers can reach directly. The limitation is not a flaw in the mission design. It accurately reflects the technology and the scale of the challenge. The missions we have are tremendously capable. They are reading Mars's chemistry in ways that were not possible before, and they are consistently finding that the planet had interesting chemistry in its past, not dead. not sterile. A serious candidate for prebiotic or even biological activity. The isotopic record also carries information that could, in principle, distinguish biological from non-biological processes. Life on Earth preferentially uses certain isotopes of carbon and sulfur in ways that leave patterns in the rock record. These patterns are used as biosignatures in the ancient Earth rock record. Mars, in principle, has the same kind of isotopic record, and some missions have begun measuring carbon and sulfur isotopes. But the signal-to-noise problem is severe at the level of sensitivity currently available in the field. Definitive isotopic biosignatures may require return samples and laboratory-level instruments. Think about what a sample return from Jezero could add. A return sample would face the best mass spectrometers, microscopes, and isotopic analysis. It would also face years of careful study by the global scientific community. Things that cannot be confidently characterized by a rover instrument can be studied with extraordinary precision in a terrestrial laboratory. The sample does not answer every question. Contamination, context, and sample limits still apply, but it elevates the quality of the investigation by a significant margin. And so the rocks remember imperfectly. They hold a filtered version of the past, but the filter is not random. It preserves some signals reliably, degrades others predictably, and obscures some in ways we can understand and partially account for. Working with that filter, not pretending it is not there, and not giving up because it exists, is what the science is doing. And the practical question at the frontier of the current work is what we can realistically expect from the missions reading that evidence right now. Curiosity and perseverance are not magic life detectors. They are more interesting than that. They are context machines. Curiosity, in Gale Crater, has spent years reading an ancient environment one layer at a time. It found evidence that Gale once hosted lake and stream environments with chemistry that could have supported microbial life if life had existed there. It found organic molecules preserved in ancient rocks. It measured minerals, textures, and radiation levels over geological time. It also tracked changing chemical conditions. And that does not mean Curiosity found life. It means Curiosity made the habitability question concrete. Before missions like this, Mars was habitable, could float too easily as a broad idea. Gale forced it into rocks. What kind of water? What kind of sediments? What chemistry? What minerals? What sequence? What preservation? Which conditions changed, and which remained favorable for extended periods? Perseverance does something similar at Jezero. It explores an ancient crater lake and delta system chosen because the setting could preserve evidence of past environments and perhaps biosignatures. It studies rocks in place, documents context, and collects samples intended for possible return to Earth. Those samples matter because some questions are too delicate for rover instruments alone. On Earth, laboratories can examine material with higher precision and more methods. They can search for subtle organic patterns, isotopic signals, and mineral relationships. They can also study textures that require careful interpretation. But even sample return would not be a magic answer machine. A returned Jezero sample could show that a specific environment had water, chemistry, and preservation potential. It might even carry a candidate biosignature that would demand serious scientific debate. What it cannot do alone is reconstruct every habitable window Mars ever had. The mission limit is scale. Mars is a planet. Rovers are local. They move slowly across selected terrains. They drill or abrade specific rocks. They infer ancient environments from exposed outcrops. Their greatest strength is also their limitation. They give us detail in a small place, and that detail is indispensable. Without it, the planet remains too broad. Orbital maps can identify minerals and landforms. A rover can see textures, layers, and grain relationships up close. It can connect chemistry to local geology. A rover turns a promising region into a testable environmental story. But the central question asks for more than one story. Was Mars habitable long enough for life to begin? That question needs local detail and planetary context. Gale can show one kind of ancient environment, Jezero can show another. Other missions and orbiters show valley networks, clays, and sulfates. Together, those records widen the picture from individual rocks to the planet itself. Climate models test whether the settings fit a plausible ancient planet. No single line of evidence is enough. Now here is the mission limit in plain terms. Organic molecules at Gale. Thrilling, because carbon chemistry survived billions of years in ancient rock. Bounded, because organics are not life and have non-biological origins. A preserved delta at Jezero. Thrilling, because deltas can preserve environmental records across geological time. Bounded, because a delta does not prove biology. Habitable lake chemistry in Gale. Thrilling, because it shows serious conditions existed. Bounded, because habitable means possible, not inhabited. And that carefulness is not a lack of imagination, the discipline that keeps the question alive. If we overclaim, we flatten Mars into hype. If we underclaim, we miss the extraordinary fact that a world now cold and dry preserved environments that genuinely belonged in the search for life. The right line is narrower and stronger. Mars had real habitable settings. Missions are helping us ask whether those settings had duration, chemistry, and preservation in the right arrangement. The mission limit is also temporal. A rover sees what is exposed now. It reconstructs what happened then. Between those moments lies deep time. Rocks were buried and altered. They were fractured, irradiated, and exposed again. A layer may record a lake, another may record drying, another may record later fluids. The rover has to untangle history from a surface that kept changing after the main event. So when curiosity or perseverance studies a rock, the question is not just what it is, the question is what part of the sequence it preserves. Was this deposited in a lake, altered by groundwater, exposed to radiation, protected quickly, changed later? Does it belong to the habitable window itself, or to the closing of the window? The mystery belongs at that scale, small enough for instruments, large enough for planetary history. Future progress may depend less on one spectacular discovery than on better ordering, dating surfaces and deposits more precisely, returning samples with exact context, comparing multiple basins across Mars. The next layer is deeper drilling, climate testing, and patterns that repeat across the planet rather than isolated anomalies. That kind of answer is slower, but it is stronger. It might tell us that Mars had sustained lake environments in some eras, but not others. That groundwater lasted longer than surface water. That organics preserve in certain mineral contexts. Or that surface windows were too fragmented to connect across the timescales chemistry needed. And there is a human patience built into this work. A rover spends days positioning and brushing, imaging and drilling, analyzing and documenting a single target. From a distance it can look slow, but ancient Mars cannot be rushed into answering. Context is earned one rock at a time. Without context, even a spectacular molecule or texture could be misread. If Mars ever gives us a credible biosignature, the reason to trust it will not be drama. It will be the years of context surrounding the sample, where it sat, how it formed, why non-biological explanations were not enough. Mars sample return is the mission that changes the terms of the investigation at the base level, and understanding why that is helps clarify what the current missions can and cannot resolve. Curiosity and perseverance are measuring instruments on wheels. They examine targets in place. Their instruments can characterize mineralogy, chemistry, and texture. They can also detect organic molecules at the scale of a rock face or a drilled core. The capability changes the investigation. No prior Mars mission had access to this level of surface geochemistry, but instruments on a rover face two constraints that laboratories on Earth do not. The first is instrument mass and power. A rover carries its entire laboratory in a compact, power-limited package. This means trade-offs. Some measurements that are straightforward in a laboratory are either impossible or severely limited in the field. High-resolution mass spectrometry is one. Transmission electron microscopy and ultra-fine isotope measurements are others. Curiosity's organic chemistry instruments are impressive, but their sensitivity and specificity are far below what a modern analytical chemistry laboratory can achieve. The second is chain of custody and contamination control. When Perseverance drills a core and seals it in a sample tube, it is beginning a process intended to send that material to Earth under conditions that preserve it for the most sensitive analyses. Getting the context right, knowing exactly where the sample came from and what surrounded it, what layer it represents, and what the local chemistry was, requires careful documentation. A sample returned without context is far less valuable. Perseverance's documentation approach is part of the sample return mission as much as the physical drilling. Imaging, mineralogy, and chemistry come before coring. Sample return would give Earth laboratories approximately grapefruit-sized amounts of carefully documented Martian rock and sediment. These would be divided and studied across multiple institutions. Some would be processed immediately with the best available instruments. Some would be archived for future analysis with instruments not yet built. The logic of archiving is sound. The value of a sample grows as analytical techniques improve. Lunar rocks returned in the 1960s and 1970s are still yielding new science today as better instruments are applied. What could sample return plausibly tell us about the life question? If samples contain candidate biosignatures, those signals could be studied in depth. Unusual isotopic patterns would matter, so would unexpectedly selective organics or mineral structures that require specific chemical processes. Multiple independent teams could apply different methods to the same material. A credible positive result would require convergence across methods, absence of contamination explanation, and consistency with the geological context. That standard is not impossible to meet, but it is demanding, and appropriately so. Extraordinary evidence is required because the claim, life beyond Earth, is extraordinary. A rover finding an ambiguous organic signal is compelling. Laboratories on Earth demonstrating that the same signal resists all non-biological explanations would be more compelling. The difference is not the data itself, but the depth of the investigation, and sample return does not require a positive result to be enormously valuable. A careful negative, samples from a well-characterized, well-preserved habitable environment that show no convincing biosignature after the best available analysis would narrow the question in a different direction. It would say that at least one ancient Martian habitable environment did not contain detectable life at the resolution we can measure. A careful negative would be a real and important scientific result. Future missions could extend the search in other directions. Subsurface access, drilling deeper than a rover can reach, perhaps several meters, could retrieve samples shielded from billions of years of radiation damage. Seismic studies could help map the interior of Mars, including potential deep aquifers or hydrothermal systems. Atmospheric sampling and dating could refine the history of Mars's atmospheric loss, which constrains the surface habitability timeline. The Mars of the missions is not the Mars of the ancient habitable windows. Today's Mars is a cold, thin-aired surface that has spent billions of years erasing delicate evidence. The missions are reading faint signals in rocks that survived that erasure. Each result, whether thrilling or negative, is not a conclusion. Each result constrains the next hypothesis. And that process is how science eventually forces an answer out of a planet that does not give its history up willingly. Build constraints, narrow possibilities, deepen context. So when we ask whether Mars had the time, we are asking whether the evidence that survived the planet's long change from wet to dry tells us enough to decide. And the honest answer right now is that the evidence tells us the question is real. It does not yet tell us the answer. So did Mars have everything needed for life except enough time? The honest answer is close, but not simple. Mars had the ingredients: water-carved valleys, built deltas, and filled ancient lakes. The chemistry was not a single clue. It kept appearing in the rocks Mars preserved. Redox conditions appeared at multiple sites across geological time. Energy was available through sunlight and hydrothermal systems. Volcanic heat and water rock reactions mattered too. In some settings, protection existed. Sediments could bury material. Subsurface environments could reduce radiation exposure. Minerals could shield fragile chemistry from the worst of the surface. The case against Mars on simple grounds, that it lacked the ingredients, does not hold. The harder problem is arrangement. Did the water, chemistry, and energy meet in the same places, along with the right protection? Did they last long enough? Did they cycle constructively? Did local environments connect across space and time, or remain isolated scenes that never influenced each other? The answer stays unresolved there. A warm, wet Mars makes duration easier, but the faint young sun and greenhouse constraints make that picture difficult to sustain cleanly. A cold, icy Mars fits the energy budget, but makes surface habitability more episodic. Local windows may solve some of the surface problems, but introduce isolation. Subsurface habitats may protect chemistry, but remain difficult to access and read. Every threshold had to be crossed together. Water, chemistry, and energy had to arrive with protection, long enough for fragile steps to accumulate. Earth crossed that threshold at least once. We do not yet know how easily, or whether life began quickly because the path is nearly inevitable, or because Earth had an unusual combination of stability and time. Mars is the nearby experiment that might help us understand the difference between a planet that came close and a planet that crossed over. But we are not yet allowed to choose between those lessons. Mars was probably a planet of habitable windows, some visible at the surface, some buried, some in groundwater or hydrothermal systems, some too brief or isolated to complete the job. Some may still be preserved in rocks we have not yet examined. The question is whether any window became more than a window. A window can warm a room for a while, but life needs the room to remain usable, or to connect to another room before the first one freezes. Mars may have opened many rooms. We do not yet know whether any became a home. The strongest answer to the title is this: Mars had enough of the ingredients to make life a serious scientific question. It had enough water-shaped history to keep that question alive across centuries of exploration. But whether it had enough continuous, connected, chemically productive time remains one of the deepest unresolved problems in planetary science. And if the surface could not hold the windows open, the next place to look is below it, beneath the radiation and the cold swings, beneath the dry red surface, where water and rock, chemistry and protection may have lasted longer than any river or lake we can see from orbit. The search continues, not because Mars has promised us life, because Mars has preserved the boundary between a world with ingredients and a world with enough time. And somewhere in that boundary, the meaning of habitability is still waiting to be read. The next natural question is what a real Mars experiment has already told us about chemistry, time, and the line between evidence and life.